Hello again. Tonight we're going to talk about something that's postulation. It's not proven science, peer-reviewed, or official theory. It's just as I look at units of measure and how certain things in physics can be broken down to a minimal multiplier. I said, well, why not the energy of photons? Because photons have a wavelength specific to their excitation within an atom. We have a great many different bands of emissions and absorptions, and they all have values that, depending upon your scale, might be fractional or might be integer. If you know about units of measure, you'll know that eventually, if you divide things down low enough and you use the appropriate scaling, that you come to a single unit of measure that everything can fit into as an integer. So we'll basically think about that. So what led me to this cockamamie scheme, as the saying goes? I was looking at the cosmic microwave background, and there are two things that came to mind. There is a thing that's in real physics, real astrophysics, called the axis of evil. You can look it up. It's different parts of our universe and how they all affect the gravitational influences of our galaxy. And by way of our galaxy, our solar system. And by our solar system, our planet. And then there is this spot where not much is going on inside the cosmic microwave background, and the temperature is colder. There's less energy there than there is throughout what is the generally uniform cosmic microwave background. So I said, well, if the energy levels can be scaled down to a common denominator, so to speak, what would that be? And that's where I came up with this. But as the saying goes, I watched something, a light bulb came on, and of course I had to connect the dots. And some people might be quietly mumbling or thinking to themselves, oh no, not again, here we go. So it's me postulating once again, tinfoil hats at the ready. So any personal comments are in square brackets. The rest of this is all postulation and analogies. So if one of these things is like the other, so we'll get into that. The way in which we detect a photon is destructively. So the photon encounters some metallic sensor, and the metallic sensor changes the photon into electrons, which results in a voltage, and that's how we know what level of energy the photon that no longer exists had. That's basically how we measure things. Is if I want to know if it's there, that's where the sensor is. Then when I convert the photons to voltage, I measure the amplitude and I know how many of what energy level photons were at the point where my sensor is picking them up. But that doesn't tell me what direction they're traveling in or how fast, because I can't determine direction. Because if I determine that they're there at all, then I have to basically absorb the photon and convert it to electrons. There's been a lot of research in measuring the energy levels or the electron volt levels of the different orbitals of different atoms and how those fall into line with certain electromagnetic radiation wavelengths, be it radio, infrared, visible, ultraviolet, X-ray, or gamma. More energy going in produces more energetic photons coming out. No disagreement in that. Yep, I agree wholeheartedly with that. Here's where the postulation comes in. We're now starting to examine atomic structure at the very small subatomic scale. And what we're finding out is we can actually now measure the progression of an electron as it changes orbital position. That's something we couldn't do before. We just presumed it based upon the energy level of the photon that we collected. But now we can do more things. So we're starting to get closer and closer to actually measuring the photon immediately upon it being emitted in order to reduce the energy level of the electron to move it back to another energy level. You can think of it as if I wanted to measure a speeding bullet, I need a very high-speed camera, and the high-speed camera comes with a stroboscopic lighting. The light's very bright and lasts for a very brief period of time, but that way, instead of seeing the bullet here and then the bullet at its destination, I can see the bullet move through space because I'm taking samples along the way. And this is what we're doing now at the subatomic level is we're looking at the interior of atoms as electrons are moving along the way. So we actually know what level of energy it takes to make them move, how far a distance from one level to the other. And this was something that up until this year, when they got the Nobel Prize for it, there was actually the Heisenberg uncertainty principle that said, we'll never, ever be able to measure the position and velocity of an electron. It's just impossible. Well, I always thought of that as, yeah, with our current technology sensors, we can't sample fast enough to get that speeding bullet in progress. Well, apparently now we can do that, at least to a much higher level than we had in the past. And so this year's Nobel Prize is like about that Heisenberg uncertainty principle. So we're now measuring the energy of a photon, not quite where it's instantiated, but after it has been instantiated before it leaves the atom itself. So we're now starting to notice that the energy level of the photon, if we measure it along the way, the energy level is changing. It eventually, as it leaves where it came from, it has a sustained wavelength, a sustained frequency energy level. But we're seeing as it first is instantiated, it's kind of moving up to a peak level. So I said, well, what would be the minimal value that would be there for all photons, all atoms, all wavelengths? There's got to be a minimal unit of excitation that the photon is taking on. I wanted to see if I could back it down to a particular value, and I went through this handbook that the U.S. National Institutes of Science and Technology have, that for particular orbitals, they will give you the wavelength in angstroms, thank you very much, of the particular elemental emission line. And then they have a common table for the atomic structure of the atoms. This takes into account energy levels of non-ionized atoms, ionized atoms, and isotopic forms of those atoms. So you'll see like lithium-2 and helium-2. So as you go through this table or handbook, you'll see that not only will they tell you every different shell level emission and its wavelength, but also not only for the base elements, but for their isotopic forms. So I said, well, there ought to be a way to come up with a number for this. And I noticed that in the measurements, sometimes they would have 3 decimal digits, and sometimes they would have 4 decimal digits. And this is because different research projects use sensors with different levels of sensitivity. So some could measure out to 4 digits, some could measure out only to 3 digits. I said, well, we're not there yet, because when we can measure out to enough digits where the last digit or two is always 0, now we know what the minimum excitation level is. We don't have that data yet, but it sounds like they're working on getting to the point where they have that data. This is what I'm actually saying. If you think about a photon when it's first instantiated, in other words, when the field finally says, I've got too much, I need to burp out something, and it burps it out, it hasn't left even the shell that it came from. It's still within the atom. Now, once it gets outside the atom, it's emitted. And once it's emitted, it has a stable wavelength based upon the energy level and the level that it came from. But if you take any waveform and you trace it back to its origin, you get a point source. The point source would be this postulated energy level that any photon, regardless of layer, regardless of atom, regardless of whether it's an isotope or not, should be able to start with this unit energy. just my postulation. And if we work it the other way and say, I have a photon, and I want to measure that photon in the smallest unit of measure of the photon, how would I know what that is? Well, collapse it back down. You know that for other things, other measurements in physics, they have these things called Planck lengths, Planck time, and such, and the finite structure constant, where if you devolve things down to their smallest measurable value, you wind up with these constants. You wind up with these, can't decompose it any further, and anything that exists, you can multiply it up from that number. So I'm looking at it the same sort of way. And as I mentioned, we have units of measure, a quantity of things. We've got the mole, but if you look down inside of things, you'll find that when we start to measure things, we can break them down to these constants, and the fine structure constant exists. That's one of them. But the Planck limits are, we have yet to divide things down far enough to reach Planck's limits, be it distance or mass or time. We're way away from those by many orders of magnitude, so there's plenty of headroom left. In the case of things like the fine structure constant, we don't really have an explanation of why the number is what it is, or the reason for that being the number. Now, we know about the speed of light. The speed of light is more of a ratio that comes out to be that specific value. So you can't say the same thing about the speed of light that you can say about the fine structure constant, because it just happens to coincide that this ratio turns out to be exactly the same as our measurements of the speed of light. We haven't done that with the actual photons. We haven't measured photons with enough accuracy to find out what their minimal unit measure is. So we have the highest possible frequency, shortest possible wavelength that we can currently measure, and that's up in the gamma radiation band, and that would be at the 0.3 zettahertz, or 3 times 10 to the plus 20 hertz. But that's frequency. In 2021, they actually detected gamma at a much higher energy level than that. To give you an idea of energy level, we measure things in electron volts, but electron volts are a very, very small number. An electron volt, it takes quite a lot of electron volts to get to 1 volt. So an electron volt is fractionally nowhere near what a volt is. But anyway, the 1.4 peta-electron volts that they measures out to quetahertz frequency, or 2.42 times 10 to the plus 29. But we have more to go than that. The sensor technology is holding us back. And even if we could coerce the photons to become electrons that we could measure, the speed at which we would have to convert the electron count into a voltage that we could then digitally read out is not there yet. We have analog to digital converters that can convert 30 billion samples per second, but they're like 8-bit samples. But that's how we measure radio energy at very, very high frequencies, is through analog to digital converters that are running very high sample rates with fewer and fewer bits per sample. So we need to improve the technology in order to measure out further. So in order to measure even higher energy gamma, we need to extend things out to if you remember the Nyquist theorem is, if you want to measure X, you need to measure 2 times X to get, so you can actually measure the curve of things. So we need to extend out to tenths of rontometers, or 1.2 times 10 to the minus 25th meters, in order to measure those wavelengths. But the Planck limit goes all the way up to 1.6 times 10 to the minus 45. So considerable headroom. We can go on advancing the technology for a long time before we bump our head into Planck. The values that we have measured in like the NIST Handbook, they're very, very, very large compared to the smallest things we can currently measure. And that even extends out to the Large Hadron Collider. The ATLAS sensors can measure only up to 3 tera electron volts, or which is a small number compared to higher energy gamma. But the position accuracy of, if we can measure the energy of a photon using the ATLAS detector, then how do we know where we measured it from? It's wherever the sensor is. And we can only pack the sensors so tightly together. And that accuracy turns out to be 7 millionths of a meter. So we've got this unavoidable headlong collision that says, I want to be able to measure faster, but how close can I get my sensors together? And that's where this 2023 Nobel Prize, as the saying goes, sheds light into a new way of doing things. The Nobel Prize in Physics for 2023, there was a team of 3 scientists that have found a way using summation of waveforms to create either continuous or specific individual pulse trains at the 250 attosecond level. That's a quintillionth of a second. We now have the ability to shine a light on electrons to get them to produce photons to tell us where they are in space. And if we know the particular atom and we know the energy level by an infrared laser that we put into the atom, we can know where the electron is going to come out from and what other layers it's going to pass. So if you go to the Nobel Prize in Physics, you'll actually see they have an image from their research that shows you a black background and you see little white dots. And the little white dots represent the movement or the velocity over time of electrons, one electron in particular. So the Heisenberg uncertainty principle that says you can't measure an electron in both position and speed is well, we're going to measure the position by the attosecond laser exciting the electron while the atom is excited by an infrared laser. And so they produce a dot. And if they keep strobing it every 250 attoseconds, they can capture the electron here, 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 as it progresses out of the core of the atom, out of the electron shells of the atom. So if they have different samples over time of the same electron, they've now discerned the energy level of the electron and where it was over multiple periods of time. With that, they can determine the velocity, the direction and the energy level and the speed. So this is something that you have to go back and look at the Heisenberg uncertainty principle as, yes, it was not possible given the sensor technology of the day, but the day has changed. And now we have the ability to use an infrared laser on a continuous beam to excite the atom. And then we can use a 250 attosecond pulse to capture the electron as it moves from shell to shell out of the atom in the form of a photon. New science, but it's been peer reviewed and it's recognized as breaking, which is the reason why this team of 3 physicists won the Nobel Prize for Physics in 2023.
Totally deserved.
Yeah, it's
I have to relearn my physics.
Well, whenever somebody says, you'll never be able to do that, I look at the technology that is being used to say, what are you measuring? And then say, well, that's as good as we can get right now. But if we improve the technology, we can maybe take that never ever and make it just couldn't originally. And if you look at some of the things we're seeing with the James Webb Space Telescope, okay, Hubble had things it could not see, it could not discern, could not individually detect. But now that we put an even bigger telescope farther out into space and add newer electronic sensing technology, there are things that we can detect in the atmospheres of exoplanets that Hubble could never hope to do. So,
in my brain, I think that electrons have a lot of leeway to run around a lot of space.
yes.
If you're going to stimulated to go from one place to another, isn't it absorbing some energy?
Yes,
Well,
it is.
You're forcing
the
it.
the infrared laser excites the atom
Yeah,
and therefore compels the electron to move
yeah.
to an outer shell or
You're forcing it to move.
a
Yeah,
theoretical shell.
yeah.
And then when it says, I've got too much energy, I want to go back to a ground state, I want to go back to a lower level, it gives off a photon. And now what we're seeing is the infrared laser excites the atom, causing the electron to move to a different shell. And we're taking attosecond exposure pictures of the electron as it's moving to the outer layer.
But you're
That's
now
incredible.
harnessing it from its free floating
Yes.
state of mind.
Well, I
Yeah.
mean, originally Bohr just had shells in mind. And when the Heisenberg uncertainty principle was applied, the shells became clouds. You know, they
Yes.
became spheres and donuts and
Yes,
dumbbells.
because from what we tested before, whenever you test the position of the electron, you have to observe that electron or that photon with the detector or the electron. So it becomes a shell of many data points, and so that's why we call it cloud. But now with this new apparatus that I'm gonna have to read, it
Yes.
shows that it's not like almost like you're not interfering, you're just observing.
Yes.
And that is totally freaky.
Yes. Well, I mean, we've in the past used beams of X-rays to actually examine the structure of atoms, and we can see like gold atoms sitting there like little spheres. Now, that's just because the X-ray radiation essentially excites the atom, and the atom produces photons, and we collect the photons as X-rays of a specific wavelength, and then we reintegrate all those samples to make the sphere of all the different atoms that are sitting there as a gold substrate. This is the same sort of thing. If you shine a short enough duration pulse of energy and that energy reflects off of something, you can actually detect something as it's moving. And what they see is the electron speed, not its velocity, its speed going from one shell to another is not instantaneous. There's an acceleration process. So
Oh.
Hmm.
Oh.
it actually accelerates to the outer level. And then when it gives off the photon, it changes its speed by a different amount on the way back in. So, like, they speed up faster on the way out,
Not a
and they
constant
return
velocity.
to their ground state slower on
It
the way.
actually makes sense if you think about from the principle of the attraction of the core
Mm-hmm.
or even gravitational symbol, because as you go higher, farther away, you have a diminished force, so you can move faster.
But we also know that the principles of electron excitation and photon emission work out in space where there's not as much gravity, and they work the same way they do on Earth. Now, if we measure them closely enough, we can actually measure the gravitational effect on the electron because that has to be taken into account. Because if your lab is on Earth and you're measuring an electron moving out to an outer shell and then back in, there's a gravitational effect there. So
Still, this is
which
amazing.
which direction was your detector? Was the electron moving horizontally or vertically? If it's moving
Yeah,
vertically, there's definitely a gravitational effect. Electrons have mass, right?
yeah.
Yes. The more we
It is
decompose science, the
amazing
more
how
we're
can
learning that
you
what we thought
know the
as
position.
impossible is now like just needed a boost in technology.
That is, I'm gonna have to read it because this is too amazing. 2 years ago, I would say no, it's not possible. I wouldn't be able to choose my chemistry class
I think
again.
it's a little thing called peer-reviewed Nobel Physics Prize.
Sure.
Yeah,
Yeah,
that
no,
gets your
I'm gonna
attention.
read it. I just I want to understand because
Yes.
what I know what to teach in chemistry,
Yep.
if the Heisenberg principle is being refuted by this new technology, I
Yep.
need to learn the effects of it.
Yep. We need to learn
That's
about
amazing.
we need to
And
learn
I
about
have to tell Eliane too.
Yes.
because she's teaching
But just
chemistry
tell her
right
that
now and she's going
she
to repeat
might
that.
want to look at the Nobel Prize in Physics for 2023 and see if there's anything worth looking at. Now, the really neat thing of this is their lab setup is a little bit bigger than a ping pong table.
Oh, one more of
It's an
those.
optical bench that has, floated mirrors, and the beams originate and they split the beam and it goes through an interference generator that causes photons at different wavelengths to overlap one another. And then when they put it through a pass filter, the pass filter pops out with 250 attosecond wave pulses because they've, interfered with one another, and all of the stuff that meshes cancels out, and all you're left with is either a continuous stream or individual 250 attosecond pulses. And you can use those to either energize things or to measure periods of time.
That's amazing.
But it's not like they needed the large Hadron Collider sized machine to do this. It's just
And
something they threw together that's on a optical
and
about the size
that's
of a
one
ping pong
more
table.
annoying apparatus that someone thought about and got a Nobel Prize. The other one, did they ever got the Nobel Prize? The one that had the ping pong table that discovered the first stars being illuminated in like we mentioned that one should get one.
I don't know that
It
one
was
won
in
Nobel.
Australia. They have like a ping pong
Yeah, and
size
I don't know that
radio
won Nobel.
telescope that
It's
was
my
measuring
understanding
the
it's
first
been peer
stars.
reviewed. It's my understanding it's been peer reviewed, but I don't think it won Nobel. I could be wrong.
Yeah, that one is another one that should have got one.
Well, who knew there was a gravity wave background? Well, until we created the instruments like nanograv for measuring it. And what did that take? Oh, we had to first find out that there were things called pulsars. No, it's little green men. In conclusion, a postulation is an aspect of the scientific method, and not all postulations pan out. It's what gets us from sticking with all that we currently know to uncovering what we have yet to learn, and correcting anything invalid along the way. Well, as our technology improves, as we start using our brains to go, what if I did this? Would it produce something I could use to discern that? That's where these kinds of discoveries come in. I was just thinking that if you fold back any photon, it has to get down to the point where it was first emitted from an atom. And when it was emitted, how fast was it moving? There's always been this presumption that a photon instantaneously begins
Yeah,
traveling at the speed of light.
yeah. They always said that.
But using the attosecond strobe light, if we can actually see that a photon accelerates to the speed of light over, let's say, less than one half the uh, radial difference between shells, then we know that, well, those photons were photons, but they weren't moving at the speed of light. They had to accelerate to the speed of light, which means an energy was imparted upon the photon and it accelerated to the speed of light.
No,
So,
no, the Nobel Prize is talking about electrons, not photons.
yes, ma'am, you are correct. But remember, this is a postulation, and what I'm looking for is when the photon is instantiated before it is emitted from the atom, does it instantaneously go from 0 to the speed of light? Now that we have a strobe light that can allow us to see things moving over very small distances at very high velocities, and we know that electrons accelerate and decelerate. They don't instantaneously move between levels. Maybe we need to find a way to measure the velocity of photons within an atom. We might find that
Okay.
they also accelerate. And if they accelerate, that means they're imparted with the energy, and something has to build up to create the velocity that is the speed of light. The base level of that would be all photons start out with the same boost of energy, and then they accelerate to the speed of light, thereby producing an emission that is their characteristic frequency or wavelength. So,
Accelerate to the speed of light. Wow.
yeah.
Yeah,
Well, there's
that,
just this. I mean, nobody wants to actually investigate what does it take to get to the speed of light because, it's instantaneous. And we
Yeah.
keep saying it's instantaneous without actually knowing it's instantaneous because we have no technology to measure, is it truly instantaneous? Well, now we have a technology that we can measure that in electrons, and we've learned that electrons do not move shell to shell instantaneously. And in fact, moving outward, they actually accelerate faster than moving inward.
I
So,
myself do not have an appreciation of the distances between shells. I don't know how big that is. Uh,
So
I would
if
like
you
to know that.
have if you have the core of a atom like hydrogen, right, in the center of a football stadium, it would be the size of
Yeah.
a football
Yeah.
size. That would be the core.
That much
The
I get.
atom, the whole atom will be the size of the stadium.
But
the
once you
actual measurement is way smaller than nanometers,
So if you know,
like
get to
picometers.
the next shell out, the next shell out,
yeah, so it's huge.
it,
It's
yeah,
like in comparison to the size of the core or the size of the electrons, it will be, immeasurable, like
No, it is
distances.
measurable.
No, like, but it will be like in human kind of way, it will be huge distances.
It's just a number.
Yeah.
That's why we have scientific notation. You can put a negative sign and a larger number there, and it will make a smaller scaled value. So don't be afraid to create the technology or use the technology to measure things.
I wonder how that thing clocks so fast. That's amazing too.
That's another thing that we have a problem with right now is our atomic clocks are based upon a certain principle, particle fountains of isotopes emitting energy at very regular intervals. But the intervals are too long for some of the things we want to measure now. So if you said, I can measure down to 1 times 10 to the minus 11 seconds. Great. What if I want to measure something that's 1/10 of that time period? Yeah, we have to find new kinds of clocks. So that's
Yeah.
why you have to continue the research smaller and smaller and smaller, measuring more and more and more.
Shorter and shorter and shorter pieces of time. Yeah.
We've got many orders of magnitude before we ever hit the Planck limit. So it's just creating technology.
The mind
And I
boggles.
bet soon enough that technology is going to end up in your pocket.
Some of it already has. The 32, well, some of it's on your wrist. The solid state timepiece that's on your wrist has a 32 kilohertz, 32.768 kilohertz oscillator in it. And that's what keeps the time period. Now, it's not a 1 second, it's 32,000 times a second. And then they integrate that up to come up with 1 second.
Yeah.
So just that's where we start. Remember, at one time we measured time using grains of sand in an hourglass. And that was just fine for its time of the day. Nowadays, you have a mobile phone that can show you a computer graphical simulation of the grains of sand in the glass hourglass.
Yeah. Yeah.
And it's using a 32 kilohertz crystal to create
Yeah.
the precise time value.
Simulate it. Yeah.
Yeah.
Yeah. The first time I saw a digital oscilloscope,
Yep.
It's a phony. It's not really the waveform. It's a constructed waveform.
It uses an analog to digital converter
Yeah.
to sample the digital data of the voltage. And remember, everything we measure is nothing more than a voltage. The way we get to watts and amps is by indirectly measuring voltage and then load. All comes down to analog to digital converters. And the analog to digital converters all come down to that Einstein guy deciding that, hey, photons, when they excite certain materials, can produce electrons, the photoelectric effect. We've got some principles that still exist today that maybe someday they'll change, just like when Einstein came along, Newton's gravitational definition was updated. Well, we're now finding that things like Heisenberg uncertainty is just a matter of we didn't have a good enough strobe light.
Sometimes it's just another way of looking at things
Yeah,
that yeah,
like,
sure.
hey, that's a nebula. No, you need better film and better telescopes. That's a galaxy. And that was, in the last century that we figured that out. Never say never in the realm of science and technology. Just say that's what it is today. But
Today.
tomorrow, and we're always looking for that base unit of measure. Can't get any smaller, can't measure it anymore. Lots of links, and those will be in the PDF. And I included the 2023 Nobel Prize in Physics. I included the press release, and in the press release is the preliminary PDF of the presentation. And then if you want to see things over time, I do have the Bohr model and current understanding of electron shells. And for those that are looking for the very large and the very small, I included the Wikipedia on metrics prefixes. So
Okay.
what's the smallest? They have 3 levels of small that we have yet to measure, but they already have the Greek word prefix for that small. I was looking at, which was it? I think it was the Large Hadron Collider. The Large Hadron Collider now has 1 exabyte of storage for its active measurements. So if you were to take a megabyte and increase that by 1,000, you get a gigabyte. If you take a gigabyte and increase that by 1,000, you get a terabyte. If you increase that by 1,000, you get a petabyte. If you increase that by 1,000, you get an exabyte. And there's like 4 other prefixes that are bigger than that. So not only are we working on the very small, we're also working on the quantities of the very large.
This is something that is impossible to comprehend. When you increase
Oh,
something,
people always want to say that.
they put the numbers in
It's
there a
just a
thousand
number.
times. A
As, as,
thousand times 5 is hard
as,
to figure.
as soon as it gets to be smaller than you can see, quieter than you can hear, a frequency that you cannot see or hear, it just becomes a number. Once it's beyond human physiology,
Yeah.
it doesn't matter. It's just a
Yeah.
number. Now, you can compare 2 numbers like what is the diameter of a gold atom versus what is the diameter of the innermost electron orbital. You can measure those things. There are digital values for that, and you can see, that level of distance, and then you can create an analogy of a softball inside of a stadium. You can create analogies to give people a feeling for. There's lots of empty space in there,
Yeah.
which takes me back to the Blues Brothers when they were driving their police vehicle through the
Yeah.
interior of the Chicago Mall.
Yeah.
What was it that Dan Aykroyd said?
Uh,
Lots of space in this mall.
yeah. Yeah.
Yeah.
Mm.
When I repeat it, you recall it. Like, yeah, lots of space in this mall. Well, atoms, lots of space in these atoms.
Yeah. A lot of nothing.
Yeah, but you need something small enough and cannot be affected by other things to fill that space. Otherwise, it's simply a matter of, well, you can't have 2 things in the same place at the same time. That's a different Heisenberg.
Yeah. I have a hard time with students who push buttons on their calculators and they get an answer, but they don't appreciate what that means. You know,
If they only knew how fractional units work in a calculator, because there are some ratios you can enter for which the calculator will not give you a finite answer, even though if you were using math and not a calculator, you would have a finite answer. And it doesn't even have to be like something with a little dash above that last 3. There's YouTube videos that go into that for the people that don't understand. And there's also YouTube videos that explain when you're mixing operators like addition, subtraction, multiplication, and division, there's an order by which they're to be executed. And
yeah.
there are some calculators that just go left to right, and that's going to produce the wrong answer. You don't want a calculator like that. You want one that actually takes into account the precedence order of the operators. That's why when I got my first opportunity to buy a handheld calculator, I bought an HP 45 because it supported reverse Polish notation.
That's right.
or
Yeah.
stacking, inverse stacking. And that you could always come up with the correct answer because they would always process in the right way.
Well, you can handwrite it out with parentheses,
Oh, no,
and
no, no. See, prior to my calculator, I used the slide rule.
yeah,
The
the number.
slide rule will only measure to the physical accuracy of the material that the slide rule is measured in, is composed of. And I couldn't afford one of the fancy vanadium metal slide rules, so I had a plastic slide rule, and it was good to 2 decimal digits, but not 3,
Yeah, yeah,
because the plastic would expand and contract under heat,
yeah.
and that would be your 3rd decimal digit. It'd be a little off.
Well, that's how we got to the moon on slide rules.
Yes. Okay, so I thought this would be a fun distraction for tonight, especially since there's a Nobel Prize. I can stand on the shoulders of giants.
By the way, you should look at the other Nobel Prizes and do other presentations too, because that was interesting. I like it.
I have done that before. Remember microscopic tweezers, optical tweezers? I did
That
do
one was
something
good.
then because people are still to this day going, you can't move things with light. Photons don't have mass. Photons may not have mass, but they have energy, and energy is momentum, and you transfer the momentum, and you can move things with light.
No, I mean this period now, the Nobel Prize of the latest.
Well, this
I
one's not
mean,
a theory, it's peer reviewed science that
no,
you
I
can,
mean, no, I didn't say theory. I mean, you could do a presentation like next from the recent Nobel Prizes being announced.
oh, well, that's what this one
Look
was.
the other ones. Yeah, look the
Yeah,
other ones.
there's historically other ones. You weren't
No,
on
no, I
those.
mean Stark, the whole week they're announcing one by one. This whole week.
Well, they've got them in mathematics and physics and chemistry and things like that.
Yeah, so look to see if there is any other one that is
Okay.
interesting as this one.
But next week is by member request. Joanne wanted something on clouds, and I was going to turn that out this week, but since the Nobel Prize announcement came out, I said, I'll take the one that's already been in the queue for a while and update it. And that's what we did tonight. And next week we'll do clouds. I'm already finding fascinating things about water
For
droplets
me,
in the sky.
when you see something that is floating in the sky and you have no idea how much mass that is in vapor of water,
Yes.
that is one of the most incredibles. And you look like that, you have no idea that a small cloud could weigh
Well,
tons.
you can measure it even more precisely than that. Last week, when I was evaluating like where you are in space and at some point in the future where you'd be in space and can you face yourself and like wave to yourself, um, where would you be in the future? And we started taking into account all of the different minutia measurements of different things, like the speed of rotation of the Earth varies at the microsecond level almost daily, plus and minus. Well, what would be something that would cause the speed of rotation of the Earth to vary? If you have rain clouds that are trapped by a mountain and the wind won't let the rain cloud move, that becomes a many, many tons of water in the sky mass that impedes the rotation of the Earth. It's not going to end your life. It's not going to change anything that you know of, but we've actually got a laser square frame interferometer that will measure the acceleration and basically measure the plus and minus acceleration of the rotation of the Earth down to the around 15 to 20 microsecond level per day.
Yeah, and if you have more evaporation, some of the
Yeah.
lakes and close Maria oceans are changing the mass, so you have lighter stuff on the surface because everything's becoming clouds. You're gonna change the rotation of the planet. That is
Yes.
kind of crazy.
Not by huge amounts, and it does vary all
Like
the
if you
time.
lose, yeah, if you lose more ice
Mm-hmm.
on the on the polar caps, you change the speed of the rotation. If you remove water from the aquifers and leave on the surface of the planet, who that then will
Yeah.
become clouds, you change the mass of the surface of the
And
planet. So
and
yeah, it is crazy that you can
yeah,
alter that.
what's the packing density of water droplets in clouds closer to sea level, like fog, versus um, altocumulus, which are predominantly ice crystals because they're so high up that they've basically frozen. So, what's the packing density difference? Well, obviously, the high altitude ice crystals are going to be farther apart. Otherwise, they would create enough mass to fall out of the sky. But that occasionally happens. Or have you not heard of hail? So
Oh hell.
it's all these nuances of just water vapor in the sky, or the fact that the fog off of California's coast that gets trapped there by the mountain range. Um, it's more water there than it is vapor in the atmosphere. That's why it condenses and wants to fall to the ground as dew, as fog. Um, as soon as you allow it to go higher, the vapor pressure is reduced because the atmospheric pressure is less. And if you ever were into cooking, you know that you have to adjust the you have to adjust the boiling temperature of water based upon the atmospheric pressure and altitude.
It's less, yeah.
Yeah. So that's why I didn't just crank out something on clouds, because I can't do that. I can't just go, I think you got 5 types. Here you go. 4 slides were done. No, no, no. I got to get into the minutia. So we'll get into the minutia of clouds next week.
That's fun.
That's why I don't make spaghetti up in the mountains.
That's why if you want to bake a cake in an oven, that you have to adjust the cooking time for the moisture in your batter. Well, chefs would know that. Moms that cook cakes would know that, especially if they lived in Denver, which is the mile high city. But everybody in Denver knows how you have to adjust the duration of cooking because everybody's living at the same altitude. Kind of like we don't adjust it here near sea level because everybody we know of lives near sea level.
So Monroe,
Yes.
it, it so this thing. Well, first of all, I was looking a little bit about this, and I read that I just saw that attoseconds are so short that the number of attoseconds in 1 second is the same, roughly, as the number of seconds since the beginning of the universe, which is amazing, amazing.
An
But
attosecond is a quintillionth of a second. So how many seconds since the beginning of the universe? A quintillion.
well, I guess a billion billion.
No, no, no. It's 5 times over. Quintillion is 5. So it's 5,000 multipliers of a microsecond.
You could really set your timing belt precisely using one of those things.
Yes, you could set an
But
alarm to wake up by.
so the orbitals are calculated by the Schrodinger equation, right? And supposedly, or apparently, what was believed until last year, this thing is that electrons disappear from one orbital and reappear in another orbital.
Yes,
But you're
instantaneously.
right, and you're saying that now that the reason that that was even theorized was because it's always a certain frequency that's given off, right?
No,
That
no,
there
no.
isn't.
It's because we had no observational technology ability to measure anything otherwise, which means we've never observed it, which means it has to happen so fast that it's instantaneous. And until you have the technology to measure it, to observe it, it is essentially instantaneous.
But even though it's moving now and accelerating,
Yep.
the 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 orbitals are still valid. It's just a
Correct.
question of not disappearing somewhere and reappearing somewhere. It just when it reaches that orbital, that's when it either absorbs a photon and then moves until it reaches an orbital, or it falls from one orbital to another and emits the photon when it reaches the lower orbital. It's just not moving instantaneously.
That's another question to be answered. When the atom is energized and the electron moves to an outer orbital and then descends to its ground state to an inner orbital, at what point is the photon emitted? Is it emitted at the point where it starts to descend, somewhere along the line, or immediately upon getting back to its ground state?
Well, at what point is the photon absorbed? And at what time is the photon emitted?
Well, the absorbed, we know, is when it's at its lower state, is when it gets absorbed, when the electron has more energy. But at what point does it give up the energy to start its journey back down? Does it do it at the outer orbital? Does it, is there any reverberation? You remember?
No, it does it at the inner orbital, because otherwise it wouldn't have enough energy to give it off, and that would make it symmetric. Of course, I'm just postulating.
I'm not against people postulating, but I would suspect that the electron gives off the photon, and therefore it no longer has the energy to keep itself out at the outer level. It comes back to the inner level because it's negative and there's protons in the nucleus and comes back in.
Oh, that makes sense.
So, but as we can now observe things, we can see stuff moving out and stuff moving back. What we cannot yet sense is at what point does the photon come out? Because the photon is what we use to measure the position and velocity of the electron. So we need some ability to measure the photon at its instantiation point versus its emission point. Is there a time difference in there? So far, much like the electron going out and back in zero time, we've said that the emission until it leaves the atom is instantaneous. Maybe we need a better flash bulb, even more so, and some ability to discern it, and we could find that what we thought isn't really how it works, but we need the instruments to do it.
Okay.
Great presentation. Great presentation.
Yes, very good. I have a question, but I want to wait until you turn off the recording.
Okay. Any more comments about tonight's presentation before I stop sharing and turn off the recording? Hearing nothing, we'll stop sharing. And